Everybody have a good holiday break? Good. Well, this is Chemistry 251, so if that's the class you're supposed to be in, you're in the right place. If it's not, you're in the wrong place. But I think most of you are here for the right reasons. So we'll move on with today's topics and go from there. So just to let everybody know, I record every one of my lectures. So the lectures will be recorded. They'll be posted after the lecture on my YouTube channel, and I'll put a link to that in the module for the day. So what you can see that we have right now, right, is syllabus, January 19th. So all of my modules in Canvas will be by date. So you'll be able to go in there. What you'll see right now, first day of class, I went ahead and posted the introductory PowerPoint. However, that will not be the norm. Okay, so usually you won't even see the module until after class, and then I'll put the PowerPoint in, I'll put the link. Okay, so that's the way that I do this. I also have a syllabus link up here that you can go in and read your syllabus. You'll see Wiley course resources. If you click on there, you have access to your textbook. So the textbook is electronic. It is available to you today as part of the first day program that we have here at the university. However, if you like a paper copy, they do make and sell paper copies of the book. So you can purchase that, but I believe that is at an additional cost. So what we're going to do today is we're going to introduce myself and the course. We're going to introduce the syllabus a little bit. I'm going to give you a little bit of an introduction as to why organic chemistry is important, and then we're going to cover just enough Chemistry 107 kind of materials that you all weren't in Chemistry 1. Many of you did not take Chemistry 107, and so there's some things that we have to just be familiar with, and we'll do some just-in-time teaching as time goes on. So I'm Dr. Doug Masterson. I'm a professor of chemistry and biochemistry. Organic chemistry is my passion from a scholarly point of view. I'm an organic chemist by training. I got my PhD in 1999, so probably before some of you were born. And did my postdoctoral work at Vanderbilt University I was there for 4 years. Came here in 2004 and have been associated with this institution ever since. I currently am Senior Associate Provost, so I actually have an administrative role. But I need to get away and be with students a little bit because the administrative stuff can take a toll. So it's nice to come to a class and talk about things that I like. And so we're going to talk about 251, which I affectionately call baby biochemistry. And by that I don't mean that to be derogatory. I mean that to actually be, you're going to get a lot of different topics. We're just not going to go into them in real great depth, okay? You're going to learn a lot of different and cool things throughout the semester. But I'm not going to hold you to the same kind of expectations that I would expect a chemistry major who's taking the regular organic sequence. Okay, so you're going to cover the same types of reactions, the same kind of concepts, but I'm not going to do it, to the nth degree. Okay, so we're really going to focus on those things that you all need to know for your major. So now you know a little bit about me. I want to know a little bit about you. So we'll go around the room, and if you would just tell me your name and your major, and we'll just go around real quick. We don't have a ton of time, so don't give too much more information than that. We'll start right here.
My name is Leticia, and my major is in dietetics and nutrition.
I'm Gretchen. My major is forensic science.
Thank you.
My name is Ebony Stevenson, and I'm majoring in medical laboratory science.
Thank you.
My name is Elijah, and I'm considering changing to medical laboratory science.
Okay, what are you currently?
Health sciences.
Okay, all right.
My name is Caitlin. I'm in forensic science.
Okay,
My name is Barrett. I'm in forensic science.
okay,
I'm Isabella. I'm double majoring in forensic biology and anthropology.
okay,
My name is Alyssa. I'm a poli-sci major.
okay,
My name is Rose. I'm a forensic science major.
okay.
My name is Cassidy, and I'm a forensic science major.
My name is Devin, and I'm a forensic science major.
Did you say Devin?
Yeah.
No, thank you.
My name is Javen. I'm a forensic science major.
Javen? You got a lot of forensic science.
My name is Jose. I'm a medical laboratory science major.
Okay,
My name is Emma, and I'm in health and didactics.
okay,
I'm Kelly, and I'm a forensic bio major.
okay.
My name is Victoria. I'm a forensic science major. I'm Nicole, and I'm a nutrition and dietetics major.
I'm Rachel, and I'm also a dietetics and nutrition major.
Okay, good.
I'm Abby, and I'm a double major in architectural engineering technology, forensic science books, and criminal justice.
Those are very different majors. Cool.
I'm Olivia and my major is nutrition.
That's Jacob, I'm a forensic science major. Name's Ethan, I'm a forensic science major.
Did you say Nathan?
Ethan.
Ethan, okay, sorry.
Madeline, I'm a medical laboratory science major. Arifetti,
Did you repeat that again?
Arifetti.
Okay, thank you.
My name is Gabriel, I'm a medical laboratory science major.
All right, well, welcome everybody. Now, I do have to say right off the top of the bat, I'm really good with faces and I'm terrible with names. So I even, if you talk to my wife, sometimes I'm like, with my kids, which one of the Annas am I talking about? I have an older daughter named Johanna, and a younger daughter named Brianna, and I struggle with them. So, but I will remember your faces. Feel free, if you see me on campus or around, to say hello. I enjoy talking with students outside of the classroom as well. I eat lunch at 11 at the Fresh, so if you run into me, don't be afraid to wave, say hi, ask a question if it is. I'm always available for that kind of thing. One of the things that I do try to do is be in this classroom at least 15 minutes before class. I do have office hours, but I find that sometimes it's just quicker to do things this way. So I really probably can't stay after class, but if you have a quick question or two during, the first 15 minutes before class starts, feel free to come up and talk while I'm setting up. No problems with that whatsoever. So glad to meet every one of you. We're going to spend a fair amount of time together this semester, and we're going to talk a little bit about this course and why it's important today. So, class information in the textbook, that's what you need, right? Again, I'm Dr. Doug Masterson. You can find me in the International Center, room 517. Does everybody know where the International Center is? Okay, it's that taller-ish building, right, over by the Liberal Arts Building and by the Baptist Student Union. So we're right in between. I'm on the 5th floor. There's a suite 517. I'm actually not in room 517, but I do have an open door policy. If I'm there and I'm not busy, feel free to come in and just talk. I may have to say, hold on just a second, I'm in the middle of something, but I will take a break to address any issues you may have. It would be best, because it can be a walk to the International Building, to go ahead and just email me and ask for a meeting, and that's perfectly fine too. You can call. Most people don't anymore. My office number is 64714. I do have open office hours on Wednesdays from 3 to 5. That doesn't mean that I'm sitting there doing nothing, but those are the hours of the week that I have set aside to, if you come into my office, I'm going to stop immediately what I'm doing, and I'm going to address your issue, unless I'm on the phone with the president of the university or my boss, the provost, okay? So those are kind of the rules, and I hope that day works for everybody. It's the only day that I could really kind of fit in with a broad area. But I'm certainly available by email, and I am certainly available by appointment, so feel free to email me and we can go from there, okay? You do need a model kit for this class. I'm showing an example of one of the fancier model kits. It's the same one that you all was listed as a required material. That one just happens to come in a nice plastic case. This one comes in a junky cardboard box, and I think the one you all are required to buy comes in a junky plastic bag. Okay, but your model kits will have pieces in them that you all can put together. We will make use of this throughout the semester, and you are allowed to use your model kit on exams and homework assignments and all that kind of stuff. So if you don't have a model kit, please get one. I recommend this one. If you know somebody that has an old model kit that isn't this one and they want to give it to you, by all means use it. I mean, model kits are essentially the same, okay? So that is the required model kit. You can get one in the plastic box from darlingmodels.com for about $28. The only real advantage to this model kit is it's got a few more pieces, and it's in a hard plastic case. So if you carry a backpack around a lot and you want to slide something in without it getting dented, damaged, it's a great model kit. You have a question?
Are they available at the bookstore?
They should be available at the bookstore. That will be in the plastic bag, but it's the same model kit. Yeah, it's just you've got to put it back. Yeah, back here.
Does it come with our books?
I don't know. Does it? Okay. With Eagle Direct it does? Okay, good.
Should we be bringing the kit to class
Yes.
every day?
Well, yes. I mean, I would keep it with you because you never know when we might want to use it, but there will be chapters where we're talking about structures where we'll be using it an awful lot. And I'll let you know when those chapters come about. But it never hurts to always have it. Okay? There is homework for the class. We are not using the online homework. Okay? I have assigned in the syllabus, and I'll show you some examples here in a moment. You will keep a notebook. And my recommendation to you is to work your homework problems after class that have been assigned, okay? So if you look in the syllabus, we'll see it in a minute, there's chapter readings and then there's parentheses with problem numbers. I have tried to keep that to a manageable number of problems for you all, but my recommendation to you all is that you get a notebook that has sheets that you can tear out and you do each problem on a separate sheet. And that way, on the day of a quiz, because I'm only going to give like 2 minutes at the end of a class for a quiz. I'm going to say turn in problem 1 point, whatever. You rip it out, put your name on it, put your ID number, turn it in, and you're done. You can walk out and you can leave. Okay? So, keeping up with your homework is a great way to do well in this class. Okay? So just that goes without saying. We'll talk a little bit more about that in a moment. Okay? But we do not do this. I don't do it online, okay? So it's all, even though you have access to online materials and problems, I want you to do it on paper. I want you to draw. I want you to tactically have to do this. This is a structural class, all right? We deal with the shapes of things and other things. So the purpose for this class, right, is to prepare you for what I affectionately call baby biochemistry 420, chemistry 420, which many of your majors require for you. And so that's the main goal. My goal is not to make you an organic chemist. My goal is to give you the tools that you need to be successful in biochemistry. And so to that end, we're going to spend a lot of time talking about acids and bases. Okay, that is the central concept in organic well, in all of chemistry. If you can understand acids and bases, you can get this. Okay, we're going to talk about kinetics, how fast things go. Okay, we're going to talk a little bit about structure, what shapes molecules have and why it matters. Okay, structure is actually everything. Structure and energy are actually everything. If a molecule has a certain shape, that means it has a certain function. Okay, you all are going to learn throughout your careers here, right? And especially when you get into biochem, when you get into some of your nutrition classes, you're going to learn that things behave a certain way. Chemicals behave a certain way. Biomolecules behave a certain way. And they do that because of their shape and what they're composed of. Okay, so it's very, very important. And we're also going to talk about reactions. We're going to talk about how you take something that you start with, that you've got in a bottle, and how you convert it into something you want. Okay, that's a reaction. And so we're going to talk about that. And your body's doing that all the time. You're feeding it chemicals through food. You're breathing in oxygen, which is a chemical. Your body is processing that into other substances. Okay, and so the reactions that we will focus on will be organic reactions, but really biochemistry is nothing more than organic chemistry and water. Okay? And so the concepts and the techniques that you learn in this class and in this lab will be valuable to you in helping you understand the biomolecular stuff that you'll be learning about in biochemistry. To this end, the course is really going to cover chapters 1 through 14 and chapter 18. We're covering a lot of stuff. But again, we're going to cover it at a very kind of shallow level, okay? So your graded work, we're going to have 3 60-minute exams. And by 60-minute, I mean the entire class time, okay? So that's really 75 minutes. We'll have 3 of those throughout the semester. Those are already scheduled in the syllabus. There are no makeup exams. In other words, let me say what I mean by that. If you're sick, you're in the hospital, yes, I'll let you make up the exam. What I'm saying is there's no scheduled alternative dates for the exam, okay? These are the exam dates. So take a look at it, take a look at your schedule. You know, if there's something that you're doing with the school that conflicts with one of them, come talk to me. We'll try to work out other arrangements. There's a final exam, which will be cumulative, and there will be weekly quizzes, okay, which come directly from your homework. You know what your quizzes are going to be composed of right now, okay? You don't know whether it's going to be on a Tuesday or a Thursday that I'm going to ask, okay, for a quiz question. But it is going to happen every week, okay, over something that we've covered. Now, I have to say this out front, just to be honest. Most students consider this course organic in general, to be a difficult subject, okay? It is based on logic. And once you get the fundamentals and you understand how to manipulate the logic, it actually starts to make a lot of sense to people. But at the beginning, it's going to be a little frustrating for some folks. And what I ask you to do is to treat it like you would a foreign language class. You know, if you've ever walked into a foreign language class and the teacher comes up here and starts talking in the foreign language and you're going, oh my God, right, what is going on? It's kind of the same way. You're going to hear me say things that you might have read about but you don't quite understand yet, and that's okay. Okay, that's the learning process when you run into these things that make you go, huh? That's your body telling you you're learning something. Okay, you should embrace it and move forward. Okay. Having said that, this class is open to discussion. If there's a topic that I've covered that I think, oh, they ought to be able to get this, and you go, whoa, ho, wait, stop me. We'll review it. Okay. So, good study habits are essential to success in this course. I do expect you to come to class prepared. What do I mean by prepared? You already know what the reading assignment is for the day. I expect you to have at least looked at those sections. Not necessarily worked the problems yet, but you should be familiar with the vocabulary that we're going to be talking about. It shouldn't be completely foreign to you when you come into the classroom, okay? It shouldn't be, I wonder what he's going to talk about today. Okay, that doesn't need to be what you do when you come into class, okay? So make sure you read the material beforehand. I've had students in the past say, I really don't learn by reading. Nobody does. Reading is one component to the learning, right? It really is there to help prime you to receive the paint that I'm going to put on your brain, right? You have to prime a wall before you paint it. You have to prime your brain before you learn, okay? So without that, it's hard for anything that I talk about to stick. Okay? And I know that takes time, and I've tried to adjust this class in terms of the number of problems that I assign, etc., to be reasonable. I know you have other classes. I know you've got other obligations. I know many of you work. Okay? I get it. I had to work when I was an undergraduate. I understand what time commitments issues can be. But nonetheless, these are the requirements of the class. Okay? The class format will be lecture and discussion. I do things by PowerPoint and board work. So I will do something on a PowerPoint and then we will work examples on the board. Okay? And I will work with you. Well, let me put it to you this way. You will work with me to answer those things that I put on the board. I rarely just put something on the board and just work it through. I will ask you all questions about what do you think will happen if I do this plus this. Okay? And that interaction helps with the learning. We will have some concepts tests that will just not be graded, okay? I may throw something on a PowerPoint and I'll say, you all get in groups of 4 or 5 and work on this for 5 minutes. And then we'll go and we'll work on it on the board, okay? So there will be an expectation of some, short periods of time, group work throughout the semester. And then, of course, the weekly quizzes, which we've already talked about. Class behavior. Hate that I have to address this, but it always has to be addressed anyway, so let's just get it out in the open. I don't take attendance per se, but if you're not here when a quiz is done, you can't turn in the quiz, right? So that's just kind of the rule. But, things happen. This is early in the morning, I get it. You couldn't find a parking spot, whatever, you're 5 minutes late. Just come in, don't make a fuss, find a seat without disrupting a bunch of people. Sit down and enjoy. So take that first available seat, don't disrupt. Make sure that your cell phones and other devices are either off or in silent mode. Don't answer a call during class, don't text during class, none of that. Believe me, what we're covering is more important probably than what's on those texts or on that phone call, okay? However, if you're expecting some breaking news, something with the family that might be of importance, and you see something coming through on your watch or whatever, you can get up and you can walk out and you can take the call out there. That's perfectly fine. Okay. During class, all questions should be directed to me, and we should have a back and forth. It might involve multiple students. That's perfectly fine. But let's be civil. And so if you disrupt the class in any way, you'll be asked to leave and forfeit your right to turn any assignments due that day. Unfortunately, I have never had to implement that last bullet point, but so let's not start this semester. All right, what everybody's interested in is course grading, right? Your quizzes. You will have 14 quizzes throughout the semester. Each one of those will be 20 points. This is homework that you're assigned to do outside. Each one of those is worth 20 points, okay? That's a fifth of a regular exam. So you can get a lot of points in quizzes just by keeping up with your homework, okay? So there will be 280 total points to the class, of the total class points due to these quizzes. You'll have 3 regular exams, 100 points each, so 300 total points. They will range from 20 to 30 questions, okay? They will be multiple choice. But they will also have spaces on the exam for you to draw, write, and do things. I expect you to use those spaces to draw, write, and do things before you pick the right answer, okay? Or the wrong answer, as the case may be. We will do these by multiple choice using what's known as zip grade, and I will give you a zip grade form every time you take an exam. Zip grade allows you to fill it out, and it allows me to take my phone and go click, and it grades it automatically for me, okay? Which is kind of cool. I can get you all grades back pretty quickly. Once the exams have been graded, I will return them to you through the laboratory. I will give them to the lab coordinator, and they will return those to you during the laboratory. The reason that I do that is because I don't want to waste valuable lecture time handing back papers. So all of your assignments that you turn into me will be handed back through your laboratory, okay? But you will be able to go into Canvas and see what you scored as soon as I get that stuff posted. The final exam is 150 points. It is cumulative, meaning it will cover every topic that we covered in the class, okay? It will be more than 20 to 30 questions. It'll be somewhere around 50, okay? You'll have more time to complete it. The good news is, since it's cumulative, if you do better on the final exam than you have done on the entire course, I'll give you the better of the 2 grades. Having said that, don't count on it. Don't think, oh, I can fail the first exam or the second exam. I'll just do better on the final, okay? So if you complete the final and you get a B on the final and I add everything up for the course and it comes out to be a C, I'll give you the B, okay? What does that mean for you? That means it is never, until the final, mathematically impossible for you to do better in this class. If it's at midterm and you've got a grade that you're not happy with, you can do better. There is opportunity for you to do better and to do the final well and to get a better grade. It is never impossible until you turn in that final for you to do a better grade in this class, okay? There will also be 25 points dedicated to participation, working in groups, that kind of thing. We will have study sessions that will occur outside of class that I will schedule before each exam. So usually, I'll take a kind of a poll. I'll schedule a couple of periods for an hour where people can just come. We can work things on the board. We can do whatever. Those will not be in this classroom. They're usually upstairs on the 4th floor. And for those of you who can't attend, I usually record those as well and then post them, okay? But you don't get the benefit of asking your own questions. You don't get the benefit of stopping me and asking for clarification. All right, so does that make sense? All right. All exams will be offset such that the highest class score is 100%, but I cap that at 10%. So exam 1, worth 100 points. If the highest exam score in this class was a 95, I give everybody an additional 5 points, okay? If the highest exam score was an 85, I only give 10 points, okay? So there is a little bit of an offset because sometimes, maybe I asked a question that a lot of you missed and wasn't quite fair. I didn't think, that has happened sometimes. So I take care of that with that. Again, the thing about no makeup exams, right? We don't have a scheduled makeup exam time. So keep all that in mind. Now, I do have an expanded grading scale from what many of your other classes are. I have always been perplexed as a faculty member, why is it that we devote, or most people should, I don't, Why do most people devote the vast majority of the grading scale to failure? Right? If you think about the 10-point scale, A, 100 to 90, yada, 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 when do you start failing? You start failing at 60%, right? I can tell you professionally that if I got 60% of everything that I ever submitted to get funded, or 60% of everything I submitted to get published, perfect and accepted, people would think I was a genius. All right? It just never made sense to me that we devoted 60% of the grading scale to failure. So what I've done is my philosophy is that, an A really means something. It means excellence. And failure really means something, right? And to me, failure means you didn't try. If you try in this class, you turn everything in, I can essentially guarantee you will pass. If you get an F in this class, you got an F because you didn't turn stuff in, you didn't come up to exams, you didn't participate, okay? So those two extremes are there, right? So to me, to get an A, you've got to have a 90 or better. To fail, you got to do below 52%. Okay? But I'll take a B down to 76%. I'll take a C all the way down to 65%. And I'll take a D down to 52%. Okay? So if you do your homework, right? Homework is 280 points. That's a pretty big percentage of the total class. Right? Do your homework, do well, work in study groups, whatever you need to do well on that homework. Don't cheat, but do well. Things will go. So does everybody understand that grading scale? This is firm, and it will not change at the end. I do not curve after that, okay? So it's important. 76 is the cutoff. So if you get a 75.4, you got a C. Okay? Now I do round if it's I use significant figure rule, so if you've got a 75.96, right, that's a 76. Okay, but a 75.2 is a 75. Okay, so I keep that scale very firm in those regards. Any questions about that? Okay. So this is what you'll find on your syllabus. You'll see the dates, okay, and you'll see what we're going to be covering. So today we're doing the course introduction. What we're kind of doing now, we're going to talk about some Gen Chem review. Right, we're going to do a little bit of that. Hopefully get through most of that stuff that we need to. We might do a little more Gen Chem review on the 24th. Just depends on how things overlap. Next week on the 24th, we're going to come in. We're going to cover all of Chapter 1. Okay, Chapter 1 is one of those that we're going to cover pretty quick. Okay. These are the problems that I will hold you responsible to for quizzes on Chapter 1. Yes, ma'am.
So the chapter 1 questions, are they due on the 24th or?
Not necessarily, no.
Okay.
The quiz is only fair after we've covered the material.
Okay.
So, I'm kind of going to give it away here, right? But since this will be the start of a new week, and I've got to have a quiz every week, right? Chances are the 26th will be a quiz over Chapter 1.
Oh, so it's like
Yeah.
just after you do the.
It's after we cover. Now, some chapters are split, we cover them twice, cover one chapter in an entire week, so half one time, one another. So I've got that broken out too. So you can see, like here, chapter 3.1 to 3.5 will be covered on the 31st. It would be fair game on February 2nd for me to come in and ask you a quiz on these questions. Okay, does that make sense?
Yeah.
Okay, good. All right. So, and you'll notice I've tried to keep it to a reasonable number. Having said that, that's what I'm holding you responsible for in the quizzes. If you've got time, work more problems, right? So if I assigned question 124, maybe the next couple of questions might be good. If you struggled with that one, maybe you want to look at another one, right? That kind of thing. Okay? You'll see that January the 25th is the last day to drop without academic or financial penalty. So if you walk out of here today and go, this isn't for me, you can drop now and not have a financial or academic penalty. It won't appear on your transcript. After the 25th, if you withdraw from this class, it will appear as a W on your transcript. Okay? So, and you are responsible for paying whatever tuition is associated with the course. So I try to put in some of those days as well. You see on February the 14th, hey, Valentine's Day, right, is exam 1. Okay, so we'll have exam 1. It's going to be chapter 1 through chapter 5.4. So all of the material that we've covered here, including what we talk about today. Okay? So you know when these exams are. You know all of them right now. So if you're thinking about taking an extra few days during spring break, look to see when we have exams, okay, before you make your schedules. Okay. I will offer review sessions before each exam. I'll announce the location and time as we get closer. I go to those with no agenda. I will walk into the room, I will have my markers in hand, whatever I need, and I'll say, any questions? Okay? I will post an example exam in a couple of days. It's an exam from way back in the day that's, you know, don't think studying that exam is going to give you all the answers for exam 1. We've changed books since then, okay? It's different order of stuff. But I will give that to you so you know kind of how I ask questions, okay? So what I'm expecting you to do on exam 1, of course, is to come in with homework problems that you've worked, maybe some things that you read in the book that aren't quite clear, and we'll work through those without an agenda. So I don't come in and say, all right, let's review everything. I just want to deal with your questions. Does that make sense? All right. All right, so let's get into some stuff about organic chemistry. So what is chemistry? Chemistry, of course, is a science. What is science? What do you think science is? Yeah.
A process of making sense of the world.
That's right. It is a process. It is the scientific method. Chemistry is a discipline of science. Physics is a discipline of science. Biology is a discipline of science. Medical laboratory science is a science discipline in science. Okay? But everybody uses the same scientific method. Okay? You learned about that probably in high school. We'll talk a little bit about the scientific method. But the point about science is that we pose questions or hypotheses that can be tested. And as we work problems on the board, you all will propose hypotheses that we will mentally test from our knowledge. In the laboratory, you all will pose some hypothesis. Okay? Sometimes we forget that it's about hypothesis and we start talking about goals and all this other stuff. But science is all about hypothesis-driven research. Okay? But chemistry is the discipline of science that studies the matter and the changes that it undergoes. That's why it's important for those of you in nutrition. You eat food, it undergoes changes, it gets metabolized into other things. That's chemistry. And you can learn that in a biology class, you can learn that in a chemistry class, you can learn that in a biochemistry class, you can learn that in a nutrition class. Okay? But nonetheless, when you break it down, it is chemistry. How do I get energy from the food that I eat? That's chemistry. How does the food that I eat get transformed into muscles and tissues? And that's chemistry. Okay? And there are two main branches of chemistry. Okay? People will say that there are more, but in reality, there's only two. There is organic chemistry, which is the topic we're going to be covering in this class. Okay? This was a term, not a coin, this was a term coined by Berzelius in around 1807. Before that, we didn't really think of chemistry. We were kind of alchemists, really, trying to make gold out of lead. Okay? But Berzelius coined this term of organic chemistry, and at that time, he said that organic chemistry was any matter derived from living things. There used to be this vitalism hypothesis that thought that anything that was organic had to come from something that was living. Okay? That is no longer true. We know that not to be true. A lot of organic compounds do come from living things, but it's not necessary. to get an organic compound. And today, what an organic chemist would say is organic chemistry studies molecules that are composed of carbon. Carbon is my favorite element. I joke with my other friends that the entire periodic table is there to support carbon because we're carbon-based life, right? And so we're going to talk about the study of organic molecules that contain carbon because they have carbon, hydrogen, nitrogen, oxygen, and maybe some of the other elements. Okay? This handful of elements from the entire periodic table are responsible for life. I call these atoms privileged atoms. Okay? They sit in this space on the periodic table where they can do almost magical things. Okay? Kind of the Goldilocks period. Not too hot, not too cold, just right. Okay? So they're reactive enough to undergo changes, but they're not so reactive that you just fall apart. Okay? That's kind of a special place on the periodic table, and that's what carbon occupies. There's the other branch of chemistry, which you largely learned in Chemistry 106, and for those of you who took 107, you learned mostly inorganic chemistry. It's the rest of the periodic table. It's stuff that's derived from non-living things. I say it's just rocks. Okay? All these rocks are there to support what carbon does. Okay? I am being a little facetious in that statement. I'm being a little funny, tongue-in-cheek. Of course, inorganic molecules are very important. You have to have certain vitamins and minerals for biology to work, right? You've got to have so much iron. You've got to have zinc and magnesium and all those kind of cofactors. We know that, right? But the vast majority of what goes on in a biological system is organic in nature. And so this is a very special place. In my heart, some people like to study this stuff, but I'm like, why do you want to study rocks? Some people do. Okay? So let's talk a little bit about early organic chemistry. And as I mentioned, there was this early belief called vitalism. And the belief went like this, that organic molecules can only come from a living thing due to some unknown vital force. So we were hunter-gatherers. We went out and we hunted something. We killed it or we gathered it, right? And the material, it was a living thing. We're now going to consume it, whether it be a plant or an animal, right? I can't go dig up protein or carbohydrates from a rock quarry, right? So it made sense at the time that this must be due to being alive, right? Made sense to early folks. But then comes along Frederick Wohler, who's considered to be the father of modern organic chemistry anyway. And around 1828, he inadvertently assumed, he did not set out to disprove vitalism, okay? But he did a simple experiment. And he observed that an inorganic compound could be converted into an organic compound. It could happen in a test tube, in a non-living system. By definition, that disproved the theory of vitalism, okay? And so what did he do? He took ammonium cyanate, which is an inorganic compound. Okay, you can get this from rocks, okay? And he placed it in a test tube with a little bit of water, which is also an inorganic compound. And he heated it. And he started to smell a familiar smell. Anybody know what that molecule is? That's urea. Where do you think urea comes from? Urine. That's exactly right. Which has a distinct smell, a distinct odor. Right? So he was able to take a rock, heat it up, and get something that we only thought could come from a living thing. Okay? This is an organic molecule. Okay? It contains carbon, hydrogen, nitrogen, and oxygen. And so that really sparked modern organic chemistry to think that we could take things from like crude oil, or we could take things from other substances and we could convert them into new substances if we understood the chemistry a little bit better. That's where modern organic chemistry started, okay? 1828, long time ago. But nonetheless, it's still very vital to talk about it today. No pun intended with vitalism. So this so-called ammonium cyanate and urea are isomers of one another. What do I mean by isomers? If you look at the elements on this side and you look at the elements on this side, you'll see that the elements are exactly the same. These have the same molecular formula. They have the same number and types of atoms, but notice things are connected differently, right? This is clearly ionic because I've got charges. This is clearly not ionic. I've got these bonds between carbon and oxygen shown. I've got bonds between carbon and nitrogen, right? And notice that all the hydrogens here are on two different nitrogens, whereas here they're just on one nitrogen. Things had to be rearranged and connected differently. These are called isomers. This is why having a model kit is going to be important. You can help keep track of how things are connected and what shape that ends up being, okay? So it's very, very important to be able to work with and build models. Okay? So, this single observation allowed organic chemistry to come into what we currently know it as today. One person in one room with a candle or a Bunsen, or not a Bunsen burner, an oil burner, taking a rock, putting it in a test tube and heating it up, spawned what is arguably, in my judgment, the most significant area of science in modern society. I think organic chemistry really is that. And you might ask, well, what do you have to back that up? Organic chemistry has been awarded more Nobel Prizes than any other science discipline ever. Everything that you all use, touch, eat, smell, has got something organic involved with it at some point, okay? Our modern way of life can't be what it is without chemistry for sure, and without organic chemistry specifically, okay? So, let's talk a little bit about structural theory, okay? You can have a molecular formula, right? C4H whatever, O whatever, but that can be connected in any number of ways. Structure is very, very important to the function of molecules, okay? So, when we're talking about structure, we're talking about the precise arrangement of atoms, how the atoms are connected together, and how they point in 3 dimensions, okay? One of you said that you were also an architectural student. Who was that? I think you're going to have a much better time, I think, because of your architectural training, understanding things in 3 dimensions. Most people, it's tough. I'm working on a two-dimensional piece of paper. What does that look like 3-dimensionally? Some people can do that in their head. I can do that in my head now. It took me a while. But for those of you who struggle with that, that's why the model kit's going to be so important. Having something in your hand that you can build and actually grasp and see is going to be very, very important in this class. Okay? So when I draw out that ammonium cyanate and that urea, you can clearly see now the differences, right? This nitrogen is connected to 4 hydrogens. This nitrogen is not connected to any hydrogens, but it is connected through a triple bond to this carbon, and this carbon is connected by a single bond to this oxygen. Very different connectivity here. Same number of nitrogens, same number of hydrogens, same number of carbons and oxygens, but connected differently. A rock, an organic molecule, okay? So structure is important because there are differences. Now, there were 3 main players, as I call them, in early structural theory. You have to remember, this was occurring before we could actually see molecules. All right? These people were having to do a lot of thought experiments and really think about how things could be with the limited amount of data that they had. And so there were 3 main ones. There was Archibald Cooper, there was Alexander Butlerov, and there was August Kekulé. And I kind of highlighted this one. I think this is the most important player of all of them, okay, in terms of this early structural theory, okay? There he is, not a particular handsome fella, but that's a picture of Kekulé. And this is a quote that you can actually go look up at the email or the web page that I have there. He was apparently neither a particularly good practical chemist nor an inspiring teacher. Story has it he bored his students to death. And in the laboratory, he was not very good at all. He could not go in and do much in the laboratory. But what his main contribution was the fact that he was trained as an architect to start with, which I find interesting that we actually have a double major in here that's doing architectural studies too. It's kind of cool, right? And he understood that a building wasn't on a flat piece of paper. It existed in 3 dimensions, right? And so that made a difference. And so his main contributions were theoretical. And he talked of a waking dream that he had on a London bus back in the day, in which he saw atoms starting to group themselves together in space to give shapes. And so in 1858, again, quite a ways ago, he postulated a couple of things about carbon that turned out to be true. Right? His little mind experiments turned out to be quite profound. And he said, you know what? Carbon sits on this place in the periodic table where carbon can form chains. It can connect with other carbons as much as it wants. That's one of the beauties of carbon that other elements can't do. If you take oxygen and you start putting multiple oxygens together, you know what happens? It goes boom. If you take nitrogen and you start putting a bunch of nitrogens together, you know what happens? It goes boom. If you take carbon and you put another carbon on, nothing happens in terms of boom. You can add more and you can keep adding more. That's the nice thing about carbon. We can make big molecules. We can make proteins. We can make carbohydrates. We can make plastics. You know, plastics sometimes will take 1 million carbon atoms and put them together. Okay, so we can do all kinds of things. So he said that, and it turns out to be right. He also said that carbon will always have a valency of 4. What does that mean? It does have to do with valence electrons, but what would he have meant at this time, a valency of 4? It means it forms 4 bonds. Carbon always likes to form 4 bonds. There are examples where carbon will have fewer than 4 bonds, but there are what we call intermediates, and they're involved in a reaction path to get to a product with 4 bonds. Okay? You can't take carbon with less than 4 bonds and put it in a bottle and set it on the table. Okay? It won't last very long. Okay? So he said carbon always had a valency of 4. And then he said this. He said the study of reaction products gives us structural information. Early scientists said, if you study the products, you don't know anything about what happened to get there. Well, that's nonsense. If I'm looking at the structure of a building, I know, right? I know something about how it was constructed. I know the material that was used. I know the shape that the building, I know that the bricklayer in here had to lay the bricks a certain way. You know, I start to know some things by looking at the final product, okay? And so these were 3 things that were very, very influential in terms of how we started to study organic chemistry and how we got to where we are today. So I say he is one of the, even though he couldn't go in the lab and do anything worth a darn, he gave us the foundation to understand how we can go in the lab and do things that we do today. Okay? Let's talk a little bit about electronic theory. Okay? Chemistry is all about the electrons. Carbon sits at a particular place on the periodic table and it has a particular number of electrons. It has a total number of electrons and then it also has valence electrons. What are more important, the total number or the valence? The valence. They're in the higher energy shell. They're the ones that are available to bump into other atoms and form bonds with, right? And so electrons really are the glue that keep all of our molecules together, okay? And in organic chemistry, for the most part, we're going to be talking about covalent bonds. What is a covalent bond?
The electrons are shared evenly.
That's right. So we've got 2 atoms that have a bond between them, and there's 2 electrons in that bond that are being shared between the 2 atoms, okay? Now, what you describe by being shared evenly is a true covalent bond. We can have different flavors of covalent bonds. We can have polar covalent bonds, where one of the atoms will kind of hog the electrons a little bit more than the other, but they're still sharing. Sharing does not always mean equal, right? I can share my cake with you, but I might eat more of it than you, right? So it's still sharing, but it's not equal, okay? And so we'll talk about nonpolar covalent bonds and polar covalent bonds as we go through, and being able to identify those is very, very important, okay? Electronic theory helps us understand reactions, right? When we are on the board working out a reaction, we are not going to care at all about the nucleus of the atom. Not at all. We're going to care about the electrons. Everything that we do and everything that we talk about is, well, this electron's going to want to do that. This electron's going to want to react with that atom. This electron's going to want to pair with that electron. You're never going to hear me say, well, I wonder what happens to the protons and the neutrons. I don't care. I'm a chemist. Do you know who cares about protons and neutrons? Physicists. They care about nuclear stuff. They do nuclear physics, right? And it's important, right? There's no doubt about it. But it's just not chemistry. Chemistry is all about the electrons. So that's the only real fundamental particle that we really care about as chemists. Reactions occur because of the electrons. Atoms move towards one another because the electrons want to do something. And I say want. I mean, it's not like they have a consciousness, right? But you get my idea. And reaction mechanisms come from electronic theory. What do I mean by reaction mechanism? It's the sequence of events. In general chemistry, you probably learned like A goes to B. But what happens in between? How does A become B? Does it just magically turn into B? Absolutely not, right? There's a process. There's multiple steps that occur. We're going to learn how you can take an organic molecule and react it with another chemical and the steps that it has to undergo to give the final product. And it's all based on logic. And it's all based on stability. Mother Nature wants to go and be lazy. Okay? So when you eat food, you're taking something complex and you're breaking it down into things that are simpler. That's favorable. Going to a higher order of complexity is unfavorable. It doesn't mean it doesn't happen. We're obviously complex, right? But you have to remember from general chemistry, there's a thing called enthalpy and entropy, right? And what I'm kind of talking about here is entropy. Things always kind of try to be more disordered, and we'll talk about those topics as well. So let's talk a little bit about the influence of organic chemistry. This is something that I think everybody at the university needs to have a little bit of understanding about. Number one, it's very important to medicine. You get sick, you go to the doctor, they give you a prescription. Chances are it's going to be an organic molecule. Unless they say, oh, you're iron deficient, here, take some iron sulfate. Okay, you can do that. But your antibiotics, organic molecules. Hormones, if you take hormones, organic molecules. Your COVID boosters, if you were taking COVID vaccines and COVID boosters, organic molecules, okay? Nonetheless, so organic chemistry's had a big, big impact on medicine, both ancient and modern. You know, if you look at old ancient remedies that actually work, most of them don't work, but the ones that actually do work, when you isolate it down to what was responsible, it's almost always an organic compound, okay? Aspirin. Right? Native Americans used to chew on the bark of the willow tree to cure their headaches. It contains salicylic acid, which is the main component of aspirin. Okay? So an ancient cure, we actually have a modern rationale. We actually synthesize. We don't go out and kill willow trees anymore. We synthesize aspirin so that we can take it. Okay? Prescription drugs, these are prepared by synthetic chemists. Pfizer, Eli Lilly, all of these companies that prepare drugs hire lots of chemists. They hire biologists and other people too, but they hire a lot of chemists because, hey, we've got this molecule that will treat this disease, and now we've got to figure out how to make it. And that's not easy, right? How many people in here have ever heard of the drug Taxol? Taxol is probably the most effective breast cancer drug in existence. It comes from the bark of the yew tree, but the yew tree contains so little of it. To treat any number of people, we would have had to have decimated that species. Okay? Well, obviously we're not going to do that. But we knew the structure of Taxol, right? They isolated it. They figured out that this could cure cancer. They figured out that what the structure of it was, how all the atoms were connected. Then they said to chemists, figure out how to take crude oil, goop, that's organic, and convert it into this molecule that cures breast cancer, okay? And that took decades to figure out. It's a complicated molecule with a lot of shapes and a lot of atoms and a lot of zigs and zags, okay? And they had to figure out how to take what they had in organic starting feedstocks, which has largely come from crude oil, and figure out how to make Taxol. And they figured it out. Okay, so now you can go and you can get Taxol prescriptions and treat cancer with it, and it has a very high success rate, actually. Okay. Dyes, believe it or not, started out in organic chemistry, right? If you think about it, a few hundred years ago, if you were wearing purple, you would have been considered royalty. It's still considered a royal color, right? Only kings and queens and other people like of that level would wear it. Because they actually had to go out and get these mollusks, I forget what they were called, they had to kill them and get their ink. And so it took lots of these little mollusks to make enough material to make, if you were a poor peasant, you couldn't afford to have purple. But now when you go into a clothing store and you see a shirt that you like and it's there in 5 different colors, chances are one of them might be purple. And do they charge you more for the purple one? Not at all. It's just a different color, right? And it's because we don't kill mollusks to get purple anymore. We make purple. We synthesize it, okay? This was the first solid link of research, chemical research, and industry. This is when they started to say, you know what? Maybe we can take some of these smart people, instead of having them teach in college, we'll bring them in and we'll have them do stuff that we can actually sell. That was what happened in the chemistry of dyes. So today, when you get your dyed eggs or whatever, it doesn't cost you more to have a purple egg or yellow egg or whatever. It's just we can make these colors, we can make them cheap because we no longer have to go out and harvest them from the natural world. Okay. And of course, materials. We have an entire school in polymer science that deals with materials. If you're interested in that, you can go take one of their classes. But what they do over there is largely organic chemistry, right? They just look at it from big organic molecules and making plastics and doing things like that. But if you think about the things that we take for granted today, like fibers, like nylon, right? You use nylon rope. It's very rugged, and you can put it on a boat. Water doesn't seem to deteriorate it. It's very strong. You cannot find nylon in nature. It doesn't exist. It's a completely person-made thing, right? You think about synthetic rubber. In the early days of automobiles, we had to decimate trees and harvest the sap of the rubber tree just to make one tire. We don't do that anymore. We make neoprene. We make synthetic rubber, okay? And then think about all of the other things that you all use, right? Everything from, you probably don't use CDs or DVDs anymore, but those are plastic, plastic milk jugs, plastic water bottles, plastic whatever, right? All of these things come from polymers, which are organic molecules. And yes, these things have created challenges for us in society, but we're trying to overcome those. But I would argue, I like living in the modern world. I like being able to have the things that I have. I like to be able to wear multiple colors of shirts without having to worry about it. I like the fact that I can go and get a prescription filled. And you all might think, my gosh, that is so expensive, that one prescription. Yeah, but you're alive. Think about less than 100 years ago, the wealthiest person in the world didn't have access to the kind of health care that we have today. And that health care today is available in large part because of chemistry, right? So massive influence of organic chemistry on our everyday lives. So where did all the carbon come from? Okay? It is believed, this is still theory, right? But it is believed it came from the Big Bang Theory, that there was a very hot, very dense point containing all matter, it exploded, the universe was created. You can imagine, actually it's hard to imagine that, right? It's pretty fantastic. And so initially nothing more than a proton or a neutron existed after the Big Bang. But shortly thereafter, these protons and these neutrons started to come together. and form atoms, okay? And so the easiest thing to think about is a proton coming together with an electron. Remember, a neutron is nothing more than a proton plus an electron, okay? So you get a proton and a neutron that, a proton and an electron come together, you get a hydrogen, you get two hydrogens coming together, and you start to form helium. We know that when we look in the universe that there is more hydrogen and helium than anything in the universe. And then this helium starts to come together through a fusion process to form carbon. Carbon is really nothing more than 3 helium atoms that happen to come together and form a new molecule. And this can happen in a dying star. We actually can observe this happening in dying stars. So chemistry and astronomy do have a connection. There are chemical astronomers that study the stars. And we do know that stars produce carbon when they're dying. And so it's believed that we are all made of stardust. That's kind of amazing to think about, I think, right? Kind of cool. Okay? So all of the carbon came from dying stars. So let's talk a little bit about the periodic table. And so where do you think I'm going to spend most of my time?
Found this on the web.
Oh, thank you. Where do you think I'm going to spend most of my time as an organic chemist? Right here? No, over here?
Yeah.
Right in here, right? This is carbon, nitrogen, oxygen. What did I say that most organic molecules contained? Carbon, nitrogen, and oxygen, and hydrogen. Hydrogen, not helium. Okay, but hydrogen. So hydrogen, carbon, nitrogen, and oxygen are going to be our principal atoms that we're talking about this semester. Everything else, I mean, we'll talk about some of these. You know, we might talk about a little bit of some of this. But most of what we're going to be talking about is this. And so I always like to think about the whole periodic table is cradling the space for carbon, right? And it's because carbon is right there at number 6. That's why it's so important, okay? Notice it's not too close to fluorine. Remember, fluorine's very electronegative. It likes to attract electrons to itself. We also know that fluorine's very reactive. It's not really close to fluorine, so it's not as reactive as maybe oxygen would be. But also notice it's a little further away from lithium as well. Lithium, if you take lithium metal, you can do a YouTube video or see the YouTube videos on this. Take a little lithium metal, throw it into water, it buzzes around and then goes pop. Right? Take some carbon, some charcoal, throw it in water. What happens? Nothing. Right? So it's not as reactive as lithium, nor is it as reactive as fluorine. It's in this sweet spot where it can accept electrons and it can also give them away. Fairly controlled. Okay? That's why life is carbon-based. Okay? And so you might wonder, well, there's more silicon in the world, in the universe, than there is carbon, so why didn't we become silicon-based? Well, it's because even though they're in the same family, silicon actually has one other layer of orbitals that can take on more electrons, that can take on different shapes. And those shapes, for whatever reason that I don't know, didn't lead to life. Okay? So, kind of cool. Okay, so as you think about the periodic table, what things do you need to remember other than where carbon sits? What other things do you think are going to be important to you? What did you learn about the periodic table when you were in 106?
Metals, nonmetals, and metalloid.
Okay, so over here we have the what? We have some metals. What do we call these? Those are the transition metals, and this area over here we call the nonmetals, and we call this the metalloids, right? They kind of start to act like a metal, maybe not. This is kind of stuff that's important for your cell phone and your computer to work. This is where we get semiconductors. Kind of cool. Notice where carbon sits. Really close to the metalloids. It's not a metal. But like a semiconductor, it can accept and donate electrons as it needs to. It can be oxidized or it can reduce. Things that are kind of important for life. Okay? So, kind of cool. What else did you know? What do we know about things that are in a group up and down like this, a vertical group? What do we call that?
Properties.
Huh?
Is your properties?
They do. What do we call it, though? What do we call that?
Column?
It is a column, but what do we call the column?
A group.
We can call it a group. What's another name for that? A family, right? So we say the oxygen family, the carbon family, whatever, right? And we know that the way that I always remember that, families stand together, okay? And so I would expect that oxygen and sulfur would have similar chemistry or similar properties, but not identical. And I know that because oxygen is a gas on Earth, sulfur is a solid, okay? So we expect it to have similar properties, but not identical. Carbon has similar properties to silicon, but not identical, so on and so forth, okay? What else do we have? What about going this way? What do we call that? Electronegativity is a result of it. You're not wrong, just not what I'm looking for yet.
Periods.
Those are periods. Do we expect the same properties in periods? No, because the valence electrons change as you go in a period. Okay? So I would expect the chemistry of boron to be different than carbon. I would expect the chemistry of carbon to be different than nitrogen. I would expect the chemistry of nitrogen to be different than oxygen, so on and so forth. Okay? What do I know if I go in this direction of the periodic table? Electronegativity, right? Fluorine is considered the most electronegative atom. Around here, we consider this to be the least electronegative. What does that mean? It means that stuff over here likes to give away its electrons. Right? That's what metals do. That's why they conduct electricity. What about over here? They want to grab electrons. They want to pull electrons to themselves. Where does carbon sit? Kind of in the middle, right? It'll give away its electrons if it needs to, but it'll also take some. Okay? And so it allows it to do these processes that are very, very important in living systems. Okay? So, you might know that, we'll just quickly cover this, right? An atomic number, right? So an atom, so X would be like C for carbon would be X, right? Where Z is the atomic number. So the atomic number for carbon is 6. That's the number of protons in the nucleus. And then we also have this thing called a mass number, which is the sum of the protons and the neutrons. Okay, so we never write Z. There's no point in writing Z, right? I don't do that. Why don't I have to do that? Why do I not have to say that there are 6 protons in the nucleus? Because there's no other thing on the periodic table that's called C. That symbol takes care of that, so we just ignore that. But there are other isotopes of carbon. There's carbon-12, which is most of the carbon in the world, meaning that it has 6 protons and 6 neutrons. 6 plus 6 equals 12. But there's also another one called carbon-13, which is heavier by 1 unit. It has 1 more neutron. Okay, so there are isotopes as well for many of these atoms. But nonetheless, what do we know about carbons 12 and 13? They do the same chemistry for all practical purposes. They have the same number of valence electrons. Okay, they just happen to have a different number of neutrons in their nucleus. Okay. So this would be an example of a concepts test. I'm going to skip that for today. You'll be able to look at that when I post this. We do need to know a little something about orbitals and energy levels. And I always thank my lucky stars every day that I decided to be an organic chemist, because I only got to deal with a couple of orbitals because of where carbon sits. What do you all know about orbitals? Pardon?
There's 4 different levels.
Okay, they're different levels. What else do we know about them? What are they? They're a what? We think of them as a shape. Yeah, that's how we think about them. But what are they really? They are nothing more than a room for electrons to sit in. That's it. And those rooms have different shapes. Okay? They are probabilities of finding an electron. That's it. Probabilities of finding an electron. Okay? And so for organic chemistry, fortunately, we typically only have to deal with these 2 levels. And I like to think of these levels, I call it the hotel model. When you go to a hotel, not a motel, a hotel, right? You go into the hotel and there are multiple levels to that hotel. Would you agree that the 3rd floor is higher in energy than the 2nd floor? right? If you jumped out of the third floor, chances are you'd die. Jumping out of the second floor, you might live. Different energy, right? Different energy. Okay? Same thing here. Except in the Atomic Hotel, the floor one only has one room that you can stay in. And we call it an S room. And it's round and it's circular. Right? I colored it red. But if we take the elevator up to the second floor, I've got an S room that's shaped like a ball, but I've also got 3 P rooms that are shaped like dumbbells. Okay? I've got different places that electrons could be. Now, when you go and stay in a hotel, typically how many people stay in a room? Typically 2. And you kind of got to like each other, right? If you hate each other, it's not going to work out very well, right? So I can put 2 occupants in level 1 in the S orbital, but they got to be spinning in different directions. The electron one has to be spinning up, one has to be spinning down. And I can do the same thing in the second level, okay? So I am going to stop there for today. We'll finish this next Tuesday. I do want to take a moment and remind you that there is an assignment due by 5 p.m. today that's in Canvas, okay? Make sure you do that, get that uploaded, don't be late, and I will get you all your grades back and comments. Yes?
How soon is the recording available?
I will have it available sometime this afternoon.
Okay, thank you.
Yep.